Hello, students. I had a couple questions out of the Module A, as it's called, Appendix A, your choice. And so under Math Connections, the questions were on number 2 and number 6. So let's take a look here at number 2. Oops, bad color there, and I don't have my cool pen, so get to live with this for a little bit. Let me get a little bit of white space here, maybe, and see if that'll help. So we're trying to explain why A, B, C, D in standard base 10 place notation is equal to A plus B plus C plus D. Mod 9. Now remember, this is a mod 9. Well, let's take a look and see if we can figure this out. Okay. So now, so the way to think about this, though, is this is in place value notation. So think about the place values of each component. So for example, when I look here, this is ones, and then you shift over one place value and you've got tens. So the C is in tens place. Next to that, B is in the hundreds place. And we'll go purple here. A is in the thousands place. So think about that. And then write that out in place value form. So ABCD is equal to 1000A plus 100B plus 10C plus D. Let me move that up. There we go. You can see that a little bit better. Okay. So now 1000, 100, 10, and 1. So now you can see if we want this, what is this equal to? Well, clearly the D is matching the D from up top. What I'm saying is right here. Those are already there, so we're good with that. Now the question is, can you show or prove that 10C is equivalent to C? Now remember, this is mod 9. So what we showed in the mod clock is that anytime you have something mod 9, like 0, 0, 9, 18, 27, 36, ... Those are all kind of in the same residue class, or kind of that same grouping. They all have the same value in mod 9. So you could do the same thing with the number 1. So the number 1, add 9, 10, 19, 28, 37, ... So 1, 10, 19, 20. So any one of these, you can replace it with any of the others because they all have the same value. So what's the big deal there? Well, 10C, notice number 10 is in this list. It has the same value as 1. So 10 is equivalent to 1 mod 9. Now, if you don't want to believe that, take a look at this. 10 is equal to what? 9 plus 1. And when you're dealing with mod 9, 9 is equivalent to 0. So this is actually equal to 0 plus 1, which, no big surprise here, equals 1. So when I see 10C and I'm thinking mod 9, I can rewrite that as just 1C. And really, this is 1D, if you want to think of it that way. Okay. Let's go over here. So 100B. Well, here's where you could use some tools from the prior class. 100. We're thinking about groups of 9 or division by 9. So you can say, well, break it down into chunks you know are divisible by 9. And so now 100 would be the same as 90 plus 10. 90, though, is going to be in this top group because it's a multiple of 9. So any multiple of 9 would be equivalent to 0. So really, this 90 that we just broke down is equivalent to 0, and 100 is actually the same as 10. But a minute ago, we said that 10 is the same as 1. So really, this, now if you want to break it down, that's fine. Break this one down, write it out. This is the same as 9. 9 plus 1. So 100B, even though it looks big and fancy and all that stuff, is really the same as what? 1B. Now I'll let you try it for 1000. but break off chunks that you know are equivalent. Any multiple of 9 is equivalent to 0. So break off your 9s. You should be able to break it down. And that is enough to show what you're being asked to show. A plus B plus C plus D mod 9. Once you have that down, I think it should give you a pretty good idea of a connection between A and B. And the reason for that is in the first question up here, there was no base listed, so we know it's base 10. The one below, it says base 5. Well, base 10, when we work in mod 9, we get to add them up. What would it be in base 5? All right, so there's a good nudge for you on that one. Next one here, Allie wants to know what elements of a 5-clock system have a multiplicative inverse. What do I tell her? So she's got a 5-hour clock system. Which ones have a multiplicative inverse? Okay, so I'm going to multiply and get the value that I want. Well, let's take a look. If this is true, okay. So you have a couple options. What elements have a multiplicative inverse? You could go through and say, well, what would I multiply? Okay, now remember, multiplicative inverse needs a multiplicative identity, and that multiplicative identity is 1. So when you do these problems, you want to ask yourself, pick a number, doesn't matter, right? We'll pick the number 2, and what do I multiply by that's going to get me to 1? Again, mod 5, so it has to be in a 5-clock system. Okay, so again, if you want to, you could think 2 times what gets me 1? That's a hard question. But you could say at any point in time, replace the number 1 by something it's equivalent to mod 5. And remember, mod 5, something it's equivalent to would be 6. And maybe this question's a little easier. 2 times what equals 6? Again, in a mod 5 system. Okay, and there you might be like, oh, well, shoot, 2 times 3. 2 times 3 is 6. So 2 and 3 are multiplicative inverses. Okay. So remember, you're thinking about on a 5 clock, right? You have like on a 5 clock, I would have a 1, a 2, a 3, a 4, and a 5, right? Well, you just did 2 and 3. They are inverses of each other. So 3 is the inverse of 2 and 2 is the inverse of 3. Let's try another number. Try the number 1. 1 times what equals 1 mod 5. And now it's not too bad. Like 1 mod 5 is the same as 1, and 1 times 1 is 1. So yeah, now we're good with the number 1. And we can try the number 4, but if you take a look, if you want, you can try the number 5, right? You can, but don't forget what we talked about in class. The GCD of 5 and 5, because 5 is my number and 5 is the clock value, is 5, which is not 1. And remember, in order to have an inverse, it has to multiply to give you a 1. Anything times 5 is going to be 5, just like anything times 0 is going to be 0. All right, so 1 is its own inverse. 2 and 3 are inverses. And 4, well, GCD is 1, so I know it has an inverse, but there's nothing else to deal with because we know that 5 does not have an inverse. So in my mind, when I look at this, I have to say, well, I feel like 4 needs to be its own inverse. And let's see if we can figure that out. So if you want to, you can say 4 times what has to equal 1 mod 5. And so you can go through and add 5s until you find something that's a nice multiple of 4. So if you add 5s, starting at 1, you'd have 1, 6, 11, 16, 21, 26, 31, 36, and so on, right? Okay, so any of these look like a nice multiple of 4, and 4 times 4 gives me 16. So I could drop a 4 right here, and 4 times 4 gives me 16, which means 4 is its own inverse, and I can put a little check mark there, and 4 is its own inverse. Now here's another way to do it. You could say 4 is equivalent to -1, which it is. -1 times what gets you to +1? Mod 5. Then maybe part of you is like, well, -1 times -1. Well, shoot, then put a -1 in there. Because -1 times -1 is 1. That's perfect. Okay, but what is -1 equivalent to in a mod 5? Well, you just add 5 to it. Once you add 5, you realize the answer is 4. So you've got plenty of different ways that you can go through and do this. So you have it. So one way is to just show the actual inverses for each of the numbers. And that's how you can prove it, right? That's how you can verify it. If you want to show it more generally, you may be able to go up here, and I'm not sure if they did a full 5 o'clock. Here it is, a 5 o'clock multiplication. So when you look across each row of a full multiplication table, and again, it has to be a full multiplication table, look across for 1, and you can see every single digit appears. That means you can divide by 1 in a 5 o'clock. Okay, let's go to the next one, the number 2. Every single digit appears, a 2, a 4, a 1, a 3, and a 5. Perfect. You can divide by 2 in a 5 o'clock. Next one up, 3. Every digit appears. You can divide by 3 in a 5 o'clock. Next up, 4. Every digit appears. You can divide by 4 in a 5 o'clock. And finally, we'll get to the last one, 5, 5, 5, 5, 5, 5, 5, 5, 5, which is fantastic with one small exception. Not every number appears. As a matter of fact, pretty much nothing appears except 5s. So this is like the worst one. Okay. So that is one option that you can have. Another way you could do it is you go and find any row that has a 1 in it anytime. If it has a 1 in it, you can divide by that number. So you can divide by 1, 2, 3, and 4 because each of those rows have a 1 in it. Remember, if you have a 1 in it, that's kind of telling you the inverse, multiplicative inverse. So a couple options there. Hopefully one of those works for you and lets you explain to the student exactly what they are looking at. And I think that was it, right? Math connections. All right. That'll do it. Off you go.